Hello, Calculus. We're in section 1.3b, more on continuity. I had to move locations because Jonas is in the middle of a Paw Patrol episode. So I did add one thing to your checklist. Make sure that when you're watching these, you're in full screen mode, so you're not distracted by something in another tab or whatever, but also that will hide when questions pop up, then it won't hide so much of the screen. So go ahead and make sure you've got everything on the checklist and then hit continue when you're ready. All right. So I would like for you to copy f of x in your notes. I'm going to force a pause on your screen in just a moment. And we want to find a value for a such that f of x is everywhere continuous. So if you can see here, I don't know what a is yet, so that's a constant I want to try to find. And what I would like for you to do first is I'm going to give you a link to a DESWS graph. And I've made a slider, so I'd like for you to kind of slide a until you think you found the correct value for a. So I'm going to give you the link to this graph in one of the questions here coming up, and you're just going to take a over here on the left and slide it until you feel like that function's continuous, okay? And then write down the value of a that you get. So again, here's the function. Go ahead, I'm going to force a pause on your screen. Go ahead and write it, and I will give you the link while I force that pause as well. All right, so keep that value of a to yourself. And now let's try to do this algebraically. Okay, so let's see if we can prove that what you got with the graphing calculator does indeed match. Okay, so let's take a look at this. This top piece here is valid for x's less than or equal to 1. So that gives me the left-hand limit, the right-hand limit, the full limit, or the function value. This is going to give me the left-hand limit as well as the function value. And then the bottom piece is valid for x is greater than 1. So what would that give me? That's going to give me the right-hand limit, okay? And remember that for a function to be continuous, I need the limit and the function value to both exist, and I need them to equal each other, okay? So in other words, I need the left-hand limit to equal the right-hand limit, so that the limit will exist, and I need the function value to also equal both of those limits, okay? So I need both pieces to equal each other here, okay? Where do we have the split? For what x's did the graph have that potential break? For x equals 1, okay? So all I need to do here is I want to make sure that the left-hand limit and function value is equal to the right-hand limit. So again, at x equals 1. So if I plug in 1 for x into the top piece, what do I get? I get 1, and I just plugged in 1 for that x, and I need that to equal the bottom piece, also at x equals 1. Okay, so if I plug in 1 for x there, I get a times 1 squared, which is 1, plus 2. So now let's solve this for a. Let's subtract 2 from both sides, so I get negative 1 equals a. Is that what you got from DESWS? So hopefully so. So when I want to make a function continuous, I simply set both pieces together at whatever x value I have that break, and then I solve for whatever letter we're looking for, in this case, a. All right, for example 2, I'd like for you to try this one on your own and bring it to class. I am going to force a pause on your screen. That is going to give you a DESWS link again to see if you want to work with it graphically first, but make sure you also show me algebraically how you're getting that value of a. All right, third and final example. I'm going to force a pause on your screen. Go ahead and copy what I have. So in this case, let's take a look at both pieces, both the top and the bottom. The top piece, what do you think that gives me? The left-hand limit, the right-hand limit, the full limit, or the function value? So this is everything except x equals negative 5, and remember that's exactly how we define a limit. It's as we get very, very infinitesimally close to a certain x value, but not necessarily reaching it, right? So this would give me the full limit. And what about the bottom piece? It's valid only for x is equal to negative 5. That would give me the function value. And remember, for a function to be continuous, we need the full limit to equal the function value, okay? So we're going to do this very similarly to how we did the previous ones. We need the limit as x approaches a -5 of f of x to equal f of -5. Okay, so I know I need to use the top piece to find the limit. Now, what x value am I looking at here? I'm looking at x equals -5. Now, when I plug in -5 for the limit on the top piece here, what do I get? It's 0 over 0. Okay, so does that mean do more? Absolutely. Let's factor this kind of, well, let's go here. So the limit as x approaches -5. If I factor the numerator, I get x plus 5, x plus 4, all over x plus 5. Okay, and if we keep working with that, the x plus 5's cancel. And if I plug in -5 to the quantity that's left, I have -1, right? Okay, now let's work with the red piece. If I plug in -5 to the bottom piece here, notice there's no x's there, okay? All that piece is constant a. Okay, so that side is a constant a, and there, once again, I've got my answer already, okay? So the strategy here was really the same. I'm still going to set both pieces equal to each other. I'm still plugging in x equals -5 for all my x's, and what I see often kind of trip students up is they're like, well, this specifically said x doesn't equal -5. Well, this piece specifically said x doesn't equal 1 either, and we still plugged in 1 there, right? Because we're looking at the limit. We're looking at what do we get when we get infinitesimally close to that piece, okay? So we plugged in -5 to both pieces. We did have to do some more work here, correct? And then we simplify until we get a value for a, all right? Okay, that is all I have today. Make sure that you put any questions or feedback in the assignment, and I'll see you all next time.